All right, so today's topic, we're going to shift gears away from the analysis one segment of the course and focus on load specification. So it will be a bit of a different pattern for the next couple of weeks. A lot of the lectures will start introducing the topic with a PowerPoint slides like this one, and then we'll shift over to skeleton notes, mainly for examples and for just other things that make more sense to write out in class together than present in presentation format. So you'll see in D2L, I have all of the lecture material is available already, and you'll see that there are some topics that will have slides and then skeleton notes attached to that afterwards. I tried to estimate the start date for each topic based on the schedule, so we're pretty on track in this class, so I expect that will be, I don't expect to see many changes to that, but just stay on top of where we're at in class and you'll be able to follow along. So before we dive into this though, any questions that you have for me on homework 5 due Monday, or anything else? Okay. So again, I won't be here next Monday, so I will be posting a recording that will introduce the topic of seismic loads. So I will encourage everyone to view that recording before Wednesday's class because it will be important. We'll be building on that on Wednesday's class. And I will post that recording probably over the weekend. So keep an eye out for that. And yeah. All right, so no questions. Great. All right. So again, kind of introducing the documents that we're going to be referring to for this portion of the class. These are the handouts that I have been giving you over the last couple days. Again, if you don't have one, if you walked in recently and you don't have the handouts, there are hard copies up here, so please grab one of each. There's 3 total. I'll also leave the extras outside of my office. There's a little box on the wall outside my office, so if anyone needs a replacement or whatever, you can come by and grab one. But I did print enough copies for everyone in the class. So, all right, so this first one is the assigned text. So we're not going to be using the textbook for this portion of the class. And then the other 2 are the ASCE excerpts. So there's the one that is smaller. It's a little bit less than 10 pages. That's the one that we're going to be focused on in today's lecture, introducing dead and live loads. The other one is focused on environmental loads. And this handout is about 40 pages long. That's what we're going to be referencing significantly starting next week with seismic loads. So we'll go over seismic, wind, snow, and rain. And that's all, except for rain, that's all included in this handout. I don't think I've made this available yet on D2L, but I will release the second version is not the right word for it. Another file, so it's basically the same handout but with my notes on it. So if you'd like to refer to that with my notes on it, that'll be available to you on D2L electronically. Now, as I mentioned last time, these documents or these excerpts come from the same document. That's ASCE 7, which is the standard for minimum design loads and other criteria, right, for buildings and other structures, mainly for buildings. This document is over 800 pages long. It is a living document, so we're constantly adding new knowledge to it. Sometimes they completely rearrange things. For example, the wind loads are covered in, I think, six different chapters or something like that right now. In a previous version, it was covered in 1 or 2 chapters. And so sometimes they just do a complete overhaul on how they organize these things. So this is just for context, right? I know these handouts seem a little lengthy, and they are, but it's kind of peanuts compared to where it comes from, right? All right, so structural loads. And if you need the handouts, they're right here. All right, so structural loads are a significant responsibility of the engineer. It's something that is still not really well built into computer programs, so it's not very well automated. There are some programs that do a decent job determining, for example, wind loads, provided that you provide the correct inputs. But it's always a good idea to kind of do this analysis separately on your own and verify whatever the program spits out. All right, so the specifications of the different types of loads, where they're located on the structure, and what the magnitude will be, those are all going to be deeply rooted in the type of structure that is being designed. So that becomes very important for every type of load that you consider, and we'll look at that. It's actually called the importance factor. That's how important it is. All right, so a little bit on codes and standards. First of all, we'll talk about the standard, since we've already introduced the ASCE 7 standard. That is a document that is developed by industry experts, and it's based on years and years of data and experience. And this document provides recommendations, right? Recommendations for minimum design loads, not requirements, right? Just recommendations. A building code, such as the International Building Code, or IBC, will typically adopt a standard like ASCE 7, maybe make some changes to it, reword it a little bit, kind of repackage it in legal terms, I guess. And then different jurisdictions, governing jurisdictions, such as a city or a state, sometimes counties have their own building codes, will adopt a version of the IBC and then maybe make their own changes to that code, all right? So once a governing jurisdiction has adopted a code or a standard, then those recommendations become requirements and they become the law. So, but again, they're still minimum requirements, all right? So you might need to use your judgment as an engineer as to whether those minimum loads that you determine using this criteria are actually sufficient for the circumstances at hand. So again, we've already introduced the ASCE minimum design loads document. The latest version that has been published came out last year, ASCE 722, but it has not yet been adopted by any codes. So ASCE 716 is the version that we will be referencing in this class. That is the version that is current in Montana. You can see the note down at the bottom. So Montana has adopted the IBC 2021, which refers to ASCE 716. So it usually takes about 3 years. There's usually a 3-year cycle with the IBC code. So we can expect a new IBC to come out in 2024. And that one will likely adopt ASCE 722 criteria. So then after that is published, then it might take a few years for states to decide, okay, yeah, we want to adopt that new code, right? So it might be several years before the newest version is actually implemented into practice. And that's just because it just takes time for the engineering community to get accustomed to the new criteria and the new recommendations. So And then also because, governments operate very slowly. So, yeah. All right. Oh, another thing that I wanted to point out before we move on while we're talking about documents. The handout that is going to replace your textbook for this portion of the class, you can see the note on the top, right? So there's certain lines or paragraphs in various sections that are highlighted in gray. Those are representing pieces of information that are beyond the scope of this class. So it's not required for you to know it for this class. It's just extra information in case you'd like to understand it a little bit more in depth. So just as a heads up. And I wrote that basically just based on how I've taught this class for the last 6 years or so. And I think it could be a very useful document to keep on hand if you think that you like structures and you want to, maybe pursue that as a career option. All right. All right, so types of structural loads. We've got dead loads, which are constant in magnitude and location, right? Those are loads that we don't expect to change much over time or move around. That typically includes self-weight of the structure. It includes any permanent equipment, utilities, lighting systems, etc. Live loads, first of all, we separate live loads according to whether they are associated with a floor or with a roof. And this is a really important distinction, which will become more apparent later on when we get to load combinations. But live loads in general are any loads that are expected to change or move around over time. So these live loads will depend on the use of the building and its occupancy category, which is a term that isn't used as much anymore, but occupancy is still relevant, of course. So examples are people, furniture, so on, right? Anything that can move around. For a roof, right, live loads would represent the weight of workers moving around up on there, any equipment that might be installed on the roof, and then sometimes roofs are occupiable, right, for like patios or whatever, so people and furniture in that situation. And then also in the live load category is impact loads. These are loads that would account for dynamic effects, for example, of equipment starting and stopping. So we probably all have experienced being in an elevator where it stops and then bounces, right? Or it starts and bounces. That is the effect of the dynamic impact of that motion starting and stopping. And if you can feel it bouncing, and if it bounces a lot, that just means that the beam, the hoist beam that supports the elevator is not as stiff as it probably should be to avoid that. It doesn't mean it's not strong enough, right? It doesn't mean it's not safe. It just means that it should probably have been designed a little bit stiffer to account for that dynamic impact. All right, so dead loads. Now, this portion of the lecture will be referring to tables found in the smallest of the 3 handouts. So you may want to follow along in that handout for the next few slides. All right, so the first table in that handout will show you the minimum design dead loads for different types of finishings, right? And it's organized by category. You've got ceiling, coverings for roofs and walls, and then on the other page you've got floors, frame partitions, and so on. And then within each category, items are organized alphabetically. So my suggestion to you as you organize your work and your files for this portion of the class, I highly recommend highlighting the categories just so they're easy to spot, because if they're not highlighted, it can be sometimes difficult to pick them out since there's no indentation underneath the main category, right? Over on the right side of the table, you can see the load in pounds per square foot. So that's just a matter of looking up the item that you have and then pulling the value from the table. So if you want Roman clay tile for your roof or wall covering, that's going to be 12 pounds per square foot for your design dead load from that particular finish, right? So I also recommend maybe using a straight edge or employing some kind of straight edge to read these values, because it can be a little bit tricky sometimes if you're in the middle of a list. Yeah?
Are factors of safety taken into account when these numbers?
No. Yeah, not in the sense of design factors of safety. So that is a concept, we'll touch on it later in a couple weeks when we get to load combinations, but that's a concept that applies to one design approach, which is allowable stress design. And then there's another design approach, which is called strength design, which uses a load reduction. Let's see, they use a resistance, a capacity reduction factor in combination with increasing or decreasing certain loads and combinations. So it's similar concept, but a little bit different. But that's where you would build something like that in, yeah, at the end of the process when you do load combinations, yeah. So going along with those lines, these loads that are presented here are considered to be service loads or working level loads. They're considered to be the actual expected loads of the structure. And in reality, of course, they're not going to be perfect, but for dead loads, they're going to be pretty well dialed in, right? All right, so the next dead load table on pages 4 to 5 is, this one provides the density in pounds per cubic foot, which I know technically is not density, it's specific weight, but they call it density, of certain materials. And these, again, are listed alphabetically. So if you're working with, a reinforced concrete slab that's so many inches thick, you can use this table to calculate the load in pounds per square foot, starting with the PCF value, right, and then multiplying it by the thickness. All right, so now the live load tables are on pages 6 to 8 of the handout. These are also listed alphabetically by use. And then you have two things that you need to check. All right, so there's the uniform load provided in pounds per square foot associated with a particular use or occupancy of that space within a building. So it's not necessarily the use of the whole building, right? It's just the use of that specific area that you're considering. You may have many different live loads applicable to a building. For example, in this room, we would probably have, let's see, we're on the ground floor, so this would probably be a live load of 100 PSF in this classroom, whereas out in the hallway, actually, let's see, I think for ground floor, I'll have to look at that. Actually, we can look at that in here. Sometimes hallways are different from the rooms that are being occupied. Let's see, so for schools, classrooms, first floor, okay, so it's the corridor, the first floor corridor would be 100 PSF. Oh yeah, so I was flipping that around. So the classroom would be 40 PSF here. And then above this floor, since this is the ground floor, they would be 80 PSF in the classrooms. And then, no, the corridors, sorry. All right, I'm thinking of a different category. All right, so the corridor, the hallway outside here would be 100 PSF. Above this floor, the hallways would be 80 PSF, but the classrooms themselves would be 40 PSF, right? And then the other item that you need to consider is the concentrated load on the far right. Not every use has a concentrated load associated with it, but if there is one, then you have to make a note of that And what that means is for any given structural element, like in the gravity system that supports that location, that region, you have to consider both the effects of the distributed load over that area, and you also have to consider the effect of the concentrated load placed so that it would cause the worst effect on that particular member. So it's not like you put a concentrated load of 2,000 pounds just in the middle of the room and be like, all right, that's one possible load scenario for the concentrated load, and then the other one is going to be the uniform load. It's not like that. You have to consider the concentrated load for every individual element that supports that area, and for every individual element, where is that concentrated load placed so that it would be the worst possible case for that element. All right, so that just kind of summarizes what I was saying. All right, so you want to check both and then ultimately use the one that generates the worst case scenario for that element. All right, and then some areas don't have a concentrated load associated with it. For roofs, all right, so one thing I wanted to point out is roofs. Most roofs have a live load of 20 PSF and no concentrated load to consider. So that's just going to be your standard roof on a typical building. There are a few other specialty types of roofs that have more or less PSF value than that. But for this class, we're only going to be dealing with standard roofs. So if you think of roof live load, you can just automatically say, okay, 20 PSF. All right, so another table that is associated with live loads is found on page 8. And this one includes just some less common types of occupancy or uses, or more specialized, more specific ones. So you can see like a bakery has a live load of 150 PSF, and so on. All right, so different types of loads that we'll look at in this class, right? In addition to dead and live, we'll get into wind, seismic, snow, and rain as well. Those are all considered to be environmental loads, and those, again, are all going to be handled, except for rain loads, will be handled by this larger environmental loads handout. Other types of environmental loads include tsunami loads, tornadoes, and floods. Those are all considered within ASCE 7, but we're not going to worry about them in this class, right? All right, so now we'll talk about live load reduction. So this part of the presentation is going along with the skeleton notes handout for this lecture. So if you want to follow along with the skeleton notes, we'll go through this page, and then we'll go through some more table information, and then we'll look at an example. Or I guess, we'll kind of go back and forth a little bit between this page in the skeleton notes handout and the tables in ASC 7 handout. A little bit of back and forth there, and then I will switch to the skeleton notes and we'll work through an example. All right. So live load reduction is referring to a process that we use to basically account for the fact that if an element, say a beam, for example, supports a really large tributary area, right? Maybe it's a girder and it has a large tributary area. The larger that tributary area is, the less likely it will be that the full magnitude of the design load that you found in the table will be applied uniformly over the entire area, right? So as we can see in this classroom, we've got 40 PSF as our design load, but we don't really have 40 PSF uniformly distributed over the whole area, right? So, and the larger that area is, the less likely it will be that it will be the case that you have that full magnitude over the whole area. So this is why we can sometimes reduce live loads for members that have large tributary areas. And the calculation for that is shown right here, where the L naught represents the value that you get from the table. And then the value that you calculate in the brackets is tied to the tributary area, right? So you see the KLLAT in the denominator, and that product, KLL times AT, represents what we call the influence area. So I'm going to show you what that looks like in a few slides. But basically, if that influence area, KLLAT, is greater than 400 square feet, then you can reduce it according to this calculation. If it's less than 400 square feet and you plug it into that equation, you're going to get a value greater than 1 multiplied by your table value. So that would make you increase your load. And we don't want to increase the loads, right? So nor do we have to, right? Because the minimum is the L naught from the design load table, unless we can reduce it for a large tributary area. So if your KLLAT is less than 400 square feet, just don't reduce it, right? If you try to reduce it, you'll end up increasing it according to this equation. All right, so that live load element factor, KLL, we obtain that from a table and a figure, which I'll show you in a moment. And the unreduced live load, again, that value is from the tables that we just looked at for live loads. So the floor design live load then would be the capital L that you calculate using this equation, right? Either equal to the reduced value or equal to the table value, depending on what your tributary area times KLL is. And the tributary area that you're considering is just going to be specific to a given element that you're evaluating, right? So a common mistake is to say, okay, here's a floor plate, a floor plan, and then what is the live load for this one particular beam? So a common mistake would be to say, here's the area of the whole floor plan, therefore I can reduce the live load on the beam by that area, right, associated with that area, but that's not true. You have to consider the specific tributary area of the element that you're calculating the live load for. So it's a piece-by-piece calculation. You can't just calculate a reduced live load for a whole floor. All right, so there are some limits that apply to this reduction. If you have a member that supports only one floor, right, so that would be pretty much any beam. There are some exceptions. Occasionally you have a large transfer beam that supports more than one floor, but in this class we won't worry about that. So any beam you can safely assume in this class will only support one floor. And then sometimes columns only support one floor, right? Then your live load has to be at least 50% of the value that you got from the table if that value is 100 PSF or less. If you have a member that supports 2 or more floors, right, many columns fall into that category, then depending on what magnitude the value is from the table, you have a different lower limit, right? So you can reduce those live loads to up to 40% of the table value if your live load is 100 PSF or less, but that limit increases to 80% of the table value if you have greater than 100 PSF live load. So here is the table that shows the live load element factor, KLL. This is found in the small handout. This is on the last page of your handout, page 9 of 9. And it's basically broken down into columns, fall into the first 4 lines, and then you got beams below that, and then kind of a catch-all below that. So for most columns, the KLL value will be 4. And for most beams, KLL will be 2. So there are some exceptions, but in this class, right, that's the thing that I want you to remember. Most columns will be 4, most beams will be 2. Now here's an image that shows, this will demonstrate the difference between tributary area and influence area. So right now we've got the tributary areas highlighted for an interior column and an interior beam, right? And you know how to recognize tributary area by now, so that should be pretty straightforward, right? Half the distance in each direction to, for the column, right? Half the distance in all 4 directions to the next supporting column. And then for the beam, half the distance on both sides to the next parallel beam at that level. The influence area will expand, right, according to that KLL factor. So for the column, it got multiplied by 4. For the beam, it got multiplied by 2. And visually, this is what it looks like. So the influence area essentially, and you can picture it pretty well on this, right? Because if there's a load, let's say there's a concentrated load, for example, even though this doesn't apply to concentrated loads, but it's useful for demonstrating. If there's a load, any type of load, over here, it's still going to affect this column, right? The column will still feel the effects of that load. But for the purposes of calculating how much load that column will be responsible for supporting, we use tributary area, right? But the influence area covers the region where, right, any load will somehow affect that column or that beam. All right, so the table at the bottom of that page then, it shows you specific examples referring to that figure, right? So on the right side, you can see the grid location of the member that they're referring to. You don't have to worry about that middle portion of the table in this class, but you know, this is just kind of useful to look at if you want to try and map what's going on in that figure to the specific elements or what would apply to that, right? All right. Questions so far? I know this is a lot of information, and the next few weeks will be, you know, packed with a lot of data to keep track of, tables and figures like this. So it's going to be, like I said, it's going to be a change of pace and a different style of learning and taking notes, etc. So got a few comments then on roof live loads, and then we'll switch over to an example. So roof live loads, we can reduce those based on 2 factors. One is tributary area, for the same reason that we can reduce floor live loads based on tributary areas. And the other reason is according to the slope of the roof, right? So logically, roofs that are steeper in slope are less likely to have the full magnitude of the design live load, right? So we can reduce live loads for steeper roofs. So the reduced live load for the roof, and this is always a little bit of a point of confusion because LR, that R doesn't stand for reduced, it stands for roof, right? So the roof live load is going to be equal to the table value, which is 20 PSF for standard roofs, times the 2 reduction factors, R1 and R2. R1 is associated with the tributary area, right? And it's calculated according to this list right here, right? So if your tributary area on the roof element, and this is again applicable to the specific roof member under consideration, right? So you have to figure out what the tributary area is for that specific member. If it's less than 200, you don't reduce it based on tributary area. If it's greater than 600 or 600 or greater, you can reduce it by 40%, right? So factor would be 0.6. If it's in between, you use this equation. For the slope, you use this set right here, right? So here F, the capital F represents the slope as rise in inches per horizontal foot. So the 12 would represent a 45-degree slope, right? So that would be the biggest reduction factor. And then if you're in between 4 and 12, you use that equation. All right. So, all right, any questions? All right. So let's look at the example then. Switch over to the notes. And I think in here there should be, okay, yeah, so in the example handout, I've included relevant pages from the ASC load handout for convenience. So we can just refer directly to that within the handout. So this first example, we are given a house with a slope of 8 inches per horizontal foot. And we're told that it's covered in asphalt shingles over 1/2-inch plywood with 2-inch rigid insulation and single ply waterproofing. So all that information is going to be relevant to the dead loads, right? The types of materials that we have. And then the slope of the roof will be relevant for the live loads. And then the last sentence is relevant to dead loads. So it says the ceiling is wood furring suspension system with a mechanical duct allowance. All right, so we're asked to find the dead and live loads in pounds per square feet for the roof. All right, and then we're looking for the live load specifically for a column that supports a 150 square foot area. All right, so just for visualization purposes, all right, we've got a slope like that. So first we're just gonna go to the table for dead loads. And that table is shown on the next page, right? So we're just gonna pull these items. I've already boxed them in red for you. So first up on the list was the asphalt shingles, so that's 2 PSF. And then we have the 1/2-inch plywood. So down here, we have plywood is listed per 1/8-inch thickness, all right? So we're gonna have to do a little bit of math since we have 1/2 inch of plywood, but it's gonna be 0.4 PSF per 1/8 of an inch thickness. And then we're gonna have 2-inch rigid insulation. So again, we're gonna have to do some math here because this is listed for a 1/2 inch thickness, all right, 0.75. And then the waterproofing is given as single ply. So we get that value of 0.7 PSF from that. And then from the last sentence, we had a wood furring suspension system. So that's 2.5 PSF. And then mechanical duct allowance gives us 4 PSF. All right, so the mechanical duct allowance, that's just a general thing that covers, you know, the HVAC systems and things like that that are usually supported by the ceiling. So I'll just list, right, the values that we noted. We had 2 PSF from the asphalt shingles. The 1/2-inch plywood was given as 0.4 PSF, and then that's per 1/8 inch. Since we have a 1/2 inch, we are multiplying that value by 4, so we get 1.6 PSF. 2-inch rigid insulation, that's 0.75 PSF from the table per 1/2 inch. And then we multiply that by 2 inches to get 3 PSF. Waterproofing was 0.7 PSF. Wood furring suspension system, 2.5. And mechanical duct allowance, 4 PSF. So adding all of that up, we get 13.8 PSF. All right, so that's for the dead load. And that applies to the whole roof. For part B, let's see. Oh, right. For part A, also ask for the live load for the roof. So I'll specify that as the dead load, and then the live load. Right, since it's a standard roof, that's just going to be 20 PSF. So that's going to be your L naught, right, from the table. All right, so then part B, we're specifically focused on a column that supports 150 square feet of the roof area. And that 150 square feet, by the way, that would be over the horizontal projection. So let's say that column was located somewhere here. The 150 square feet would be based on the horizontal projection of whatever that tributary area is, right? So you wouldn't need to worry about, the slope of the roof in calculating the tributary area. But in this problem, it's given to you. But I just wanted to comment on that as to where it comes from. All right, so live load on the column. So first we've got our equation for the roof live load as L naught times R1 times R2. And since we know it's a roof, it's going to be 20 times R1 and R2. So the tributary area is given as 150 square feet. Can we reduce it according to tributary area? Right, it has to be at least 200, right? So R1 is equal to 1, no reduction based on tributary area. Slope of the roof, though, will allow us to reduce it because slope of the roof is 8. So that falls in the in-between category, which, back to slides there. All right, so we'll use that equation, 1.2 minus 0.005 times F. Or 0.05 F, not 0.005. Where F is 8, we'll go ahead and plug that in. So that's going to be 0.8. So the reduced roof live load is 20 times 1 times 0.8, which is 16 PSF. And there are some limits to check. I don't think I pointed that out earlier, but this is important, right? So you can't reduce your roof live load to below 12 PSF, and you don't need to make it any greater than 20 PSF, right? So just verify that those limits are met. All right. Questions? Okay. All right. I'll give it a minute for folks that are still writing. All right, so the next example then, we'll look at an interior column that's below the second floor of the library, all right, with a tributary area of 200 square feet, where that area is designated for a corridor. We're asked to find the design live load force on the column from that second floor corridor. All right, so first we'll look at the table for live loads. So that's going to be table 4.3-1, and I've got that on the next page for us, right here. So we're looking at libraries, right, and then corridors above the first floor. 80 PSF. Over here, no concentrated load to consider, so we've just got that 80 PSF. Hold on. Nope, I take that back. Something's off with my eyes today. All right, so concentrated load of 1,000 pounds to consider, all right? And then I want to point out too, in these two middle columns of this table, you can use this to gauge whether live load reduction is allowed just based on the use of, based on the magnitude of the L naught, right? So that doesn't determine whether, the tributary area is sufficient, of course, but just based on the magnitude of L naught, it'll tell you, can you reduce the live load? All right. So we've got library corridor above first floor. It's 80 PSF. Is the L naught value. And then since we're considering an interior column, we need to find the KLL factor. So from table 4.7-1, which should be on the last page here, we look for interior column, right? KLL is 4. So we want to check if it's reducible. All right, since KLLAT, all right, is going to be equal to 800 square feet, which is greater than 400 square feet, that's okay. All right, so that's 4 times the given 200 for AT. So we can reduce it according to the tributary area. And since the table value is 80 PSF, which is less than or equal to 100 PSF, that's also okay. So this second item is the one that you could check by looking at that column in the table where it says, is it reducible? All right, so now we calculate that reduced load. Using the formula. All right, plugging in the values, we've got 80 times 0.25 plus 15 over square root of 800, which gives us 62.4 PSF. And then you want to check the limits. All right, so we're told here that the column is below the second floor of a library. We're not told whether that column supports more than 2 floors. We don't know how many floors are in that library. So a conservative assumption, as far as the limits go, would be that the column only supports 1 floor. I know class is done. If you bear with me for just a minute. We got L then has to be greater than 0.5 times L naught, which is 40 PSF. And we do meet that criteria, right? So 62.4 is greater than the lower limit. And then the design force will be the 62.4 PSF times the tributary area of 200 square feet, or 12,480 pounds. Now, this is where you would check it against the concentrated force in the table, right? So I'll just say check against design point load. Right, is that greater than or equal to 1,000 pounds? Yes. So final answer, 12,480 pounds. Questions? All right, well, thank you for bearing with me in that extra minute there. And have a great weekend. I will see you next Wednesday. So keep an eye out for recording.